Hello everyone, my name is Professor Oaks and this video is about related rates. So here is the first example here. Now, before I even start though, you should sort of think of this section on related rates as being an application of implicit differentiation, all right? So at least if you are in that mindset that we are going to be using implicit differentiation, then these problems will be somewhat easier for you. So here's an example. Given that dy dt, so pay attention to the variable that we are finding the derivative with respect to here, is equal to 5. Find dx dt when x is equal to 1 for the equation y equals 8x squared minus 20x. So we want d dt of y equals 8x squared minus 20x. All right, so the derivative of y with respect to t is dy dt. The derivative of 8x squared with respect to t is 16x dx dt, and then the derivative of 20x with respect to t is 20 dx dt. All right, now we could actually write this right-hand side of the equation as just 16x minus 20 dx dt. And we were given that dy dt was 5, so we have 5 is equal to, now we were given x is equal to 1, so 16 times 1 minus 20 dx dt. So 16 times 1 minus 20 is negative 4, so I have 5 is negative 4 dx dt. Then I'll divide by negative 4, so negative 5/4 is dx dt, which is what we were being asked to find. Now let's do another example. Given that dx dt is equal to 8, now again pay attention to the variable we're finding the derivative with respect to, and dy dt is what we want to find when x is equal to 3 and y is equal to 4 for the equation x squared plus y squared equals 25. So I'll find the derivative with respect to t. So the derivative with respect to t of x squared is 2x dx dt. The derivative with respect to t of y squared is 2y dy dt. And the derivative with respect to t of 25 is 0. We're given that dx dt is 8. We're given that x is 3, so 2 times 3 times 8, plus we were given y is 4, so 2 times 4 dy dt is equal to 0. So 2 times 3 times 8 is 48. So 48 plus 2 times 4 is 8. So 48 plus 8 dy dt is equal to 0. Subtract the 48 from each side. So 8 dy dt is equal to negative 48. Then divide by 8 on each side. So dy dt is negative 48 over 8, or that will be negative 6. All right, so now, hopefully you enjoyed that example. Now it is time for a few more, well, I don't want to say more difficult examples, but different types of examples that will rely on the concepts in these first two problems here. So air is being pumped into a spherical balloon so that its volume increases at a rate of 100 centimeters cubed per second. So I'm going to actually write this as, now, 100 centimeters cubed per second. The seconds are a measurement of time, all right, time in seconds, and the centimeters cubed is a measure of volume. So a good notation for this would be dV dt. How the air being pumped in the balloon is changing. All right, so it's changing so that the volume of the balloon is changing at this rate. All right, so how fast is the radius of the balloon increasing when the diameter is equal to 50 centimeters? So this is what we're given. All right, so we're given dV dt is 100, and we want to find, I'll just call it dr dt, and r will be radius. All right, so this will be for the radius when the diameter is equal to 50 centimeters. But I'm going to change this so that it's also in terms of the radius. So if the diameter is 50 centimeters, then the radius is actually equal to 50 divided by 2, which is 25 centimeters. So this setup is similar to the setup of the two problems we just did, but we had to write down the notation ourselves. Now we still need to find the equation. So because this was a spherical balloon, we know that, hopefully at least, the volume of a sphere is volume V is 4/3 pi r cubed. Now, we just find the derivative with respect to t on each side of the equation. So dV dt will be 4/3 pi, and then the derivative of r to the third with respect to t is 3r squared dr dt. But we were given that dV dt is 100, and the 3's divide out, so we have 4 pi, and the radius was 25, so 25 squared dr dt. Now, we know that 25 squared is going to be 625, so 100 is 4 pi times 625 dr dt. So then 4 times 625 is 2500, so 100 is 2500 pi dr dt, then divide by 2500 pi. So 100 over 2500 pi is equal to dr dt. Or if I divide out by 100, 1 over 25 pi is dr dt. And if I want to use a decimal approximation, I can, and that would be about 0.0127. If I want to know the units, the radius was in units of centimeters, and the time was in units of seconds. So this will be centimeters per second. All right, so hopefully that all makes sense, and you really enjoyed this example here about the spherical balloon. And now it's time for a fairly classic related rates problem. So this one is about a ladder that is 10 feet long, resting against a vertical wall. So here, let's say, is the wall, and the ladder here, all right, is 10 feet, and it's resting right against the wall. If the bottom of the ladder slides away from the wall at a rate of 1 foot per second, so this is the ladder, all right, and this is the ground, and I'm going to label it ground just so that we're all clear, and this is a right angle here. All right, so the bottom of the ladder is sliding away from the wall, so it's going this way at 1 foot per second. How fast is the ladder going down the wall, this way, down the wall, when So the ladder is 6 foot from the wall. So we're given that we want to know when this distance down here on the ground, and I'll just call that G, is equal to 6 foot from the wall. All right, so what we actually have here then, if I call this, let's just say it's dg dt for the amount of distance with respect to time that the the ground is changing at here, and then I'll call this dw dt. And if you want to give this one a variable name, you could call it L for ladder and dl dt. All right. So how can I relate these variables? Well, you can think of this as being given dg dt equals 1 foot per second, that we want to find dw dt when g is equal to 6 for L equals 10, a 10-foot ladder. Okay, so keep that in mind that this is a similar setup to what we have been doing before, but we need to find an equation to relate the three variables together. The G for the ground, the L for the ladder, and the W for the wall. Well, this is a right triangle, so we can use the Pythagorean Theorem. So G squared plus W squared is L squared. Then I'm going to find the derivative with respect to t here. So this is actually 2g dg dt plus 2w dw dt equals, now remember the ladder was 10 foot no matter what, so that actually is 0 because the length of the ladder is not changing. The distance on the ground might be changing and the distance on the wall might be changing, but the length of the ladder cannot change. So that would be 2L dL dt. But because the dL dt is 0, because the length of the ladder is always 10 and the derivative of the 10 is 0, this is 0. All right, so now we have 2 times the g, which is 6, and then dg dt, which is 1, plus 2 times the w. Now, by the way, we can find w because, look at this, g squared plus w squared is L squared, but g was 6 and w was missing, but L was 10. So 36 plus w squared is 100. W squared is equal to, when I subtract 36, 64. Then I take the square root, and since the length going up in the wall there cannot be negative, w is equal to 8. So 2 times 8 dw dt. So 2 times 6 times 1 is 12. 2 times 8 is 16. So we have 12 plus 16 dw dt equals 0. Then I subtract the 12, so 16 dw dt is negative 12. Then I'll divide by 16, so dw dt is negative 12 over 16, and that reduces to, when I divide out by a factor of 4, negative 3 over 4, but the height that the ladder is up the wall is in feet, and the time was in seconds, so this is 3/4 feet per second that the top of the ladder is sliding down the wall when the bottom of the ladder is 6 feet from the wall. All right, so let's try another example here. This one will also involve the Pythagorean theorem. I will give you a heads up on that. And a lot of the classic related rates problems actually do involve the Pythagorean theorem. All right, so car A is traveling west at 50 miles per hour. So here is north, and here is south, and here is west, and here is east, just for our purposes. All right, if you want to be realistic, you might need to point your computer screen or whatever you're looking at this video on in a different direction. Although, if you think about though, right, if let's say that the car is going straight up in the air and that really is north for me, then who knows what's going on, right? All right, so let's say that car A is traveling west at 50 miles per hour, so I'll call this dA dt, 50 miles per hour. And car B is traveling north at 60 miles per hour, so I'll call that dB dt, and that will be 60 miles per hour. And both are headed for the intersection of two roads. So here is the intersection that these two cars are headed for. At what rate are the cars approaching each other? All right, so here is the distance that the cars are away from each other. So I'll call that, well, C. This is the distance the cars are away from each other. So at what rate are the cars approaching each other when car A is 0.3 miles from the intersection? So A is 0.3, and car B is 0.4 miles from the intersection. So B is 0.4. Well, this is actually very similar here because I need to find dC dt. All right, well, this is a right triangle here again, so let's find C first. So A squared plus B squared is C squared. So if A is 0.3 and B is 0.4, then we have 0.3 squared plus 0.4 squared is C squared. So 0.3 squared is going to be, let's see, that will be 0.09, and 0.04 squared will be 0.16, and that's C squared. So 0.09 plus 0.16 is going to be 0.25. So that's equal to C squared. Then when I take the square root, C will be equal to 0.5. All right, so C is equal to 0.5. Now I need to find the derivative. So d dt of A squared plus B squared equals C squared. So this will give us 2A dA dt plus 2B dB dt equals 2C dC dt. This problem is actually a little bit different than the last one because in the last problem, this hypotenuse length of the triangle was constant because it was a ladder that was a constant length of 10. However, this distance is changing when the cars move, all right? So that is the difference here. So A was 0.3, so we have 2 times 0.3 times dA dt, which is 50, plus 2 times B, which is 0.4 times dB dt, which is 60, equals 2 times C, which is 0.5 times dC dt. So 2 times 0.3 times 50 is 30. So 30 plus 2 times 0.4 times 60, that is 48. And 2 times 0.5 is 1. So 1 dC dt is just dC dt. And then we have 30 plus 48 is 78. So 78 is dc dt. And we know that all of these rates were in miles per hour. So we have 78 miles per hour, or just 78 mph. All right. So hopefully you enjoyed that example. And if you want to get a couple of friends together and have car racing towards intersections, you have to do that at your own risk. I don't endorse that at all. This is just a made-up related rates problem. Please remember that and keep your own safety in mind at all times. All right, so what a time to be alive. So here is another example. A water tank has the shape of an inverted circular cone. So I'll draw an inverted circular cone right now with a base radius of 2 meters. So here is radius is 2 meters and height of 4 meters. So here we go. This is what the inverted circular cone looks like. So water is being pumped into the tank at a rate of 2 meters cubed per minute. So the volume, dV dt, is 2 meters cubed per minute. Find the rate at which the water level is rising. So you want to find the dH dt when the water is 3 meters deep. So when h is 3. So you want to know, right, at what rate is the height changing when the height is 3, all right, 3 meters. So now let's actually go ahead and rewrite this as we usually would. So we're given that dV dt is 2 meters cubed per minute. So we want to find dH dt when h is 3 meters. So keep that in mind that this is a very similar problem to all the other ones, but we had to decipher what the words were saying ourselves. But we do need to find the equation for the volume of a cone now. So the equation for the volume of a cone is going to be, volume is 1/3 pi r squared h. Now, you see that there are actually, all right, only two variables here that we have, v and h, along with the t for a third variable. But if you try to introduce the r, that's a fourth variable. So let's try to, before we even actually get any further, try to just write this in terms of only the v's and the h's. All right, so let's look at this actually as a right triangle here. And if I do that, then I can see that, oops, here we go. I don't actually know what's going on with this whiteout. Okay, so we have a right triangle with an r is 2 and an h is 4. Right, so h is 4, but you know what? I'm going to write the h is 4 over here so that it's a little bit more clear, because remember, h was the height. All right, so now if the h is actually 3, then what would the r be? Well, we can set up a proportion for these right triangles, and we see that the the radius is half of the height. So that means in this case, if the height was 3, the radius would be 1.5. But for any, all right, for any height, or okay, if this is r, for any height, it is actually 2 times the radius, or the radius is the height divided by 2. So if I substitute this here, the height divided by 2, I have v is 1/3 pi height divided by 2 squared times height. So v is 1/3 pi. I'll square this, so h squared over 4 times h, or v is 1/3 times a fourth is 12, so pi over 12 times h to the third now. All right, so now I can find the derivative with respect to t. So dv dt is equal to pi over 12 times 3h squared dh dt. And we were given that dv dt is 2. So 2 is pi over 12 times 3 times h we were given should be 3. So 3 squared dh dt. And 3 times 3 squared is 27. So we have 2 is equal to 27 pi over 12 dh dt. Then I'll multiply by the reciprocal to get 2 times 12 over 27 pi is equal to dh dt. So 2 times 12 is 24. So 24 over 27 pi is dh dt. And I can reduce this by dividing by a factor of 3. So 8 over 9 pi is dh dt. And that's approximately, all right, I'll just write it all out. All right, 0.282942121. And then remember that this is going to be the height being measured in meters and the time in minutes, so meters per minute. What a time to be alive. I hope that you enjoyed this and got a lot of use out of seeing an example of water being pumped into a tank that's the shape of an inverted circular cone, because I knew I got a lot out of this. Once I can go to the beach, I will take a tank with me and fill up all of the water so I can swim in beach water at home. How about that? All right. So now, number 5 here. A man walks along a straight path at a speed of 4 feet per second, and a searchlight is located on the ground 20 feet from the path and is kept focused on the man. At what rate is the searchlight rotating when the man is 15 feet from the point on the path closest to the searchlight? So let's draw a diagram for this. All right, so let's say that here is the straight path that the man is walking along. So straight path, and I'll just call it X. All right, X, or you could call it P for path. It doesn't really matter. But if this is X, then dx dt is 4 feet per second. All right, and here is the man walking, and I'll give him a little bit of hair and some hands and some feet. Actually, those look more like pitchforks, and I'll give him a name. How about Howard? All right, so now a searchlight is located on the ground 20 feet from the path. So here is the searchlight, right, searchlight, and the searchlight is 20 feet from the path. So here is the 20 feet. So 20 feet from the path, and is kept focused on the man. So that means that if it's focused on the man, here it is. Right, Howard is in the light. All right, so now at what rate is the searchlight rotating when the man is 15 feet from the point on the path closest to the searchlight? So this is actually the point closest to the searchlight. And so we want this to be x is equal 15 feet. All right, so that's the point closest to the searchlight, and we want to know at what rate is this rotating. So this is the theta. All right, so this is going to be the angle of the that this is moving. All right, so we're moving this searchlight back and forth. All right, so now that means that the rate at which the searchlight is rotating is d theta dt. All right, so keep that in mind. So now we need to think of this as what we're given and what we want to find. So we are given that dx dt is 4 feet per second, and we want to find d theta dt when x is equal to 15 feet. Well, this is a right triangle, so we can actually set up an equation here if we would like that involves the x and the theta. So here we go. What is it? All right, now remember the searchlight is not moving. All right, so this is a constant. The searchlight is not moving. It's Howard who is moving because he's trying to escape the searchlight or whatever he is doing over there with his pitchfork hands. So now the tangent of theta then is x over 20 because this is the opposite side and this is the adjacent side to the theta on the triangle. All right, so then the fact of the matter is that we can find the derivative with respect to t of tangent of theta equals x over 20. So that is secant squared theta d theta dt is equal to 1 over 20 dx dt. So now think about this. I know dx dt, but I don't know theta. But I can find theta because the tangent of theta was x over 20, and x was 15 feet here, so tangent of theta is 15 over 20. And so then theta is the inverse tangent of 15 over 20. All right. So now that is the inverse tangent of 15 over 20 is 3 over 4. All right. So now all we need to do is substitute all of this into the equation that we got for the derivative over here. So we have secant squared of theta, which is tangent inverse of 3 over 4. D theta dt is 1 over 20 times dx dt, which we found to be 4. So 4 over 20 is actually, what is this? This is going to be 1 over 5. And then I just go ahead and divide by secant squared of the tangent inverse of 3 over 4. So d theta dt is 1 over 5 secant squared of the tangent inverse of 3 over 4. And then using a calculator, all right, this is about 0.128 radians per second. So I just keep that in mind as well, that this is in degrees about 7.3 degrees per second or so, something like that. So if you think about what 7 degrees actually looks like, this isn't really much of a tilt, but it's enough to make sure that the spotlight continues to be focused on Howard as he plans his escape path over there. All right, so I really hope that you enjoyed this video about related rates and that you are already looking forward to the next one. Thank you and have a great day.